the deformation pattern. Okay, that is the, I'm going to write down here. That is the deformation pattern. Okay, and I'm going to sketch around the green line. Over here, this is known as our neutral axis. Okay, that is our neutral axis, right? So when that's the case, right, at point A and point B, right, in order to have a bending this way, we need to have a moment acting in this direction. Right? If you are at home now, take a ruler and twist your hand, your fingers in that direction, you have a smiling face deformation. Okay, now the formula to use is equal to, so over here, the moment is about the z-axis. Why the moment is about the z-axis? Because if you look at the radius of curvature, the radius of curvature is the same as our z. Exactly the same like when I was teaching you guys on buckling. Exactly the same. Okay. So from here, you can see that stress X is equal. Now you have to include minus mz over izz multiplied by y. You'll see that now. Right? Okay. So now, y minus. Okay. So if we were to look at how the structure is deformed, there's a red dot down here, right? The red dot down here represents the center of curvature. Why this is important? Because if there is a center of curvature, pointing towards the center of curvature, right? Towards the center of curvature, Z is negative. Sorry, Z is positive. Pointing away from the center of curvature relative to the neutral axis, Z is what? Negative. Sorry, not Z. What am I talking about? Y. Come on, Yuji. So Y is negative. Over here, Y is positive. Okay, so pointing towards the center of curvature from the neutral axis, right? Y is positive. Pointing away is negative. Okay. Now, if we're going to have 2 points, okay, if we're going to have 2 points, so we have a point over here known as our alpha point, and we have a point down here known as our beta point. So if we were to focus on our formula, okay, before we go on, okay, I hope you all will agree that at the top, right, because it's under what? Going through what? Because the moment is acting that way, we know that this is going to be in what? Compression. The top is going to be on compression. And the bottom, right, is been stretched. So the bottom will be in what? In tension. You can see that now, right? Right. So if we were to apply the formula now, right? If we were to apply the formula, alpha, so we want to find stress X at point alpha, and we know, that Y from the neutral axis is what? Is positive. So therefore, stress X at point alpha is equal to minus mz, right? Now, the y value is positive y, and then divide by izz. So what we have is this will be equal to what? Minus mz multiplied by y divided by izz. The fact that you have minus over here means it's in what? Compression. Okay. So now, let's now look at stress X at beta now. Okay. So stress X at point beta, okay, and, right, Y now is become what? Negative. Why Y at beta is negative? Because relative to the neutral axis, Y is pointing, the distance Y is pointing away from the what? Center of curvature. When that's the case, when you write this out, stress X at point beta is equal to minus mz. Now you have minus y, and then you have izz. Minus minus is equal to plus, multiply mz multiplied by y over by izz. So this case, this is in tensile. Now let me teach you an easier way, okay? The head of the moment vector is always in what? Compression. The tail end of the moment vector is always in what? Tensor. Easy. You don't need to worry about this formula when you apply this concept. The head of the moment vector is always in compression. The tail end of the moment vector is always in tension. So I write down here, okay, apply new concept. Is the head of the moment vector is always in compression, and the tail of the moment vector is always in tensor. Are we clear? Okay, so you don't need to worry about the plus minus, pointing which direction is positive, pointing away which direction is negative. You don't need to worry about that anymore. You just focus on the moment vector. Okay, that is so much an easier concept than anything else. Okay, so now I'm going to now deal with a simpler problem. Not a simple example. Before I go on to a simple example, I like to elaborate something. Okay, because I realize students make a lot of mistake over time. Okay, now if we have a structure like this, and because we are going to rely on the moment vector, okay, the moment vector must be positioned outside the body of the structure. Okay, body of the structure, or outside the structure. Okay, this is very important. What do I mean by that? Okay, watch this. So now it is normal using right hand rule that this is x, this is y, and this is rotation about z. If we were to use this point over here, right, moment about z, you can do moment about z like this. Yes or no? Relative to the center of the point, right, this is in one direction. Okay, the important thing is this is valid, this is correct. Why? Because it's outside of the structure, this is wrong, right? Because you push it inside the structure. right? So when this is the case, over here, this is going to be compression. This side is going to be what? Tensile. You cannot have it in the body of the what? Of the structure. So for this arrow, this one is in the body, okay, in the structure. Are we clear? This is very important when applying this concept. Likewise, if you have a dot on the left hand side, let me change color. Okay, so if you have a dot on the left hand side, okay, then we do the same direction of rotation, right? We do this. So over here, this is not valid, okay, because it's in the what? Structure. You have to draw it outside the structure. So this case, this is under compression. This is under tensile. Are we clear? Right? You cannot draw it in the structure. You have to draw it out in the open air. Okay, it depends on where you analyze. Are we clear? If you're going to use your movement vectors, you have to be very clear about this. Then you don't need to worry about positive or negative or not. It can be really confusing. Okay. Now, then the next thing that I like to talk about is what do we mean by symmetrical and unsymmetrical, right? So we want to address we're going to address, right, centric symmetrical bending and what is known as symmetrical and unsymmetrical. Okay, so the next thing that we're going to focus on is what is symmetrical. Okay, what is symmetrical? And unsymmetrical bending. Okay, so I'm going to draw two different loading condition. Okay, I'm going to draw two different loading condition. So loading condition number one, where you have a simply supported beam. Okay, so one end and the other end, and you have a load. So this is omega, and the load is stopped at point. This is our point A, point B. Okay, this is our point B, and this is our point C, and we have a distance from here to here, L over 2, and then we are going to have a point load over here, P, and the distance from here to here, this is L over 4. Okay, so this is loading condition number one. Then we look at loading condition number two. Okay, we look at loading condition number two. So loading condition number two now is slightly different. Loading condition number two is slightly different. So it is a cantilever beam. Where you have a point A over here. And then you have a point B over here. And then you have a gradient distributed load. So for the gradient distributed load, you have omega down here. Okay. So I'll draw a transformation. They see the same transformation. So this is our X and this is our Y. This is rotation about Z. Now the next thing I'm going to draw, okay. We are also going to draw the